Modern computers all use 2's complement notation for binary integer values. In the past, some machines used 1's complement. The arithmetic is slightly simpler with 1's complement in most cases. But 1's complement has both a positive and negative zero, so it can get complicated. 2's complement has only one representation for each number, so it's easier to work with in the long run. As you know, with a binary integer, the first bit is the sign bit. If it is 1, the number is negative. If it is 0, the number is positive. You can reverse the sign of a number by changing all the 1 bits to 0 and all the zeros to 1 and then adding 1. This example starts off with an integer set to the value of 852. The tilde operator is the 1's complement operator. It changes all the 1 bits to 0 and all the 0 bits to 1. Then 1 is added. The process is repeated then, a 1's complement, and then adding 1, and the value comes right back to where it started. Here's what happens when you run it. You can see that taking the 1's complement of a positive number results in a negative number that's off by 1, but adding 1 results in the correct negative value. To switch the sign the other way, the same procedure is followed. Take the 1's complement, which results in a value off by 1, and then adding 1 to it brings it back to the original number. This dual operation of complement and add is what happens internally when you use a minus sign to negate a number. Take a look at this operation. Here the two integers a and b are used with the exclusive OR operator. First, A is exclusive ORed with B, then B exclusive ORed with A, then A is exclusive ORed with B again. The values of the two integers are displayed both before and after this operation. Here's what happens when you run it. Values of A and B are swapped. It's the only way I know of to swap the contents of two variables without using an intermediate storage location. When you shift bits in an integer, you need to know what's going to happen. When shifting to the leftmost bits are lost and 0 bits are introduced on the right, whether or not the number is unsigned. However, the way those numbers are interpreted is a bit different. These two integer values, one signed and one unsigned, are both shifted to the left by 2 positions. That should double the number twice. Multiply it by 4. But remember, bits on the left are being lost. The bit pattern of the two numbers is the same, but you can see that the negative number was multiplied by 4 as expected, but the unsigned number simply reduced its value. That's because it was already at its maximum possible value, so any change will reduce it. In this case, zeros were introduced in its lowest valued bits, so it was reduced by 3, the 1's bit and the 2's bit. Shifting to the right has a different effect. The shift operator acts differently for signed and unsigned numbers. The rightmost bit is lost for both signed and unsigned, but for a signed number, the leftmost bit is duplicated to fill the new vacancy. For an unsigned number, a 0 is inserted. The result is that this time the negative value doesn't change, while the unsigned value is divided by 4. None of this is mysterious, but you need to understand how the shift operators work so you won't be surprised by their actions. You can define your own special sizes for integers. You do that by defining inside a struct an int or an unsigned int followed by a colon and the number of bits it is to contain. This is most often done to match the layout you read from a file or from a device where the data items are packed into odd numbers of bits. In this example, you can see integers defined for the lengths of 1, 3, 2, and 6. Notice the integer length of 6 doesn't have a name. You can do this to insert fillers and line the data items up. All the declarations must be an int or an unsigned int, except the special case of the Boolean types. Notice that the first integer in the struct, the one named x, doesn't have a length specified for it. It's a standard int in whatever is the default size for this compiler. Once you have defined your integers, you can work with them the same as you would with any integer. In expressions, the smaller defined ints are converted to regular ints for calculation, and the ints are automatically trimmed to the size before they're stored back into memory. Notice the last statement in this example. In the struct is a 32-bit integer followed by a total of 13 bits of special sized integers. Well, the overall size is 8 bytes. The first 4 bytes are the 32-bit integer, and the other integers take up a total of 32 bits. The compiler pads out the rest of the struct, so it's not necessary for you to fill out the struct to define the bits that you're not going to use. This is not something you'll use very often, but when you do need it, this approach is certainly nicer than masking and shifting to get and set smaller bit fields.